to find the inner product of two vectors, u and v. And what the inner product is just, usually you'll see it u dot v, where u and v are n by 1 vectors. In this case, they're 2 by 1 vectors. But if you just think of these as a matrix, n by 1 matrices, then if we just take u transpose times v, still a vector, but u transpose v is defined to be the dot product. Sometimes it's called the inner product. So u dot v for this case is equal to u transpose, which we just write it as a horizontal vector, times v, which is 3 times, or 3, 5. And so you just do, your matrix multiplication, -4 times 3 plus 4 times 5, and we get -12 plus 20, which is 8. And if we were to continue to find it for like u dot u, that's going to come into play a lot, where you find the dot product with itself. So u dot u would be -4, 4 times -4, 4. And notice we'll get -4 squared plus 4 squared. It's going to get us 32. And see how that's always going to be positive, because if you've got a negative component, you're going to square it with itself, so it'll become positive. And just a few properties of dot product that might help out a little bit. If it is commutative, so u dot v is equal to v dot u. It is associative with addition, so u plus v, if you add two vectors together and then you find the inner product with another vector, you get the same thing as you take the first vector and find its inner product with w, and then add the second one to its inner product with w. So just our basic distribution property. And then we also have associativity. If c is a constant, then c acted on u dotted with v is going to give you the same thing as if you act on c with u dot v. And it's also going to give you the same thing as acting u on CV. So basically you can move that scalar in and out. And then we've already noticed that when you find the dot product with itself, it's always going to be positive. And another little thing is the only time that the dot product is equal to 0 is if you're talking about the 0 vector. So I'll say that over here. U dot u equals 0 if and only if we're talking about the 0 vector. Our problem here is to find a unit vector in the same direction as the vector v, the given vector v. And there's a couple things we need to know first. First, the length of a vector. Is notated by 2 bars on either side, but basically what the length of a vector is just the distance that it falls from the origin. And it is notated, or it is found, by taking the square root of the inner product of the vector. All right, so, and then we would say the length squared is equal to v dot v. All right, so if we find v times v, then what we have is the length squared. And another word for length that you'll hear sometime is the norm. So the norm, or the length, is basically, just if you have a vector emanating from the origin, it's the distance of the ray. Okay, so first we want to find the length of v. And as we say, the length of v is going to be the square root of v, the inner product of v with itself. So in this case, that would be 1, -2, to 0 times 1, -2, to 0. So we have 1 squared plus -2 squared plus 2 squared, and that turns out to be 9. All right, so, well, we'll say the square root of all that, square root of that. And so the length of our vector is 3. Okay, so that takes care of the length, but the question is to find a unit vector in the same direction. Okay, now what is a unit vector? And a unit vector is just a vector with a length of 1. All right, so the unit stands for the 1 part. And the easiest way to think about it is, okay, let's say that this were our vector v emanating from the origin. We've already found that the length of that is 3. So a unit vector in the same direction would be this guy right here. So it's just, multiplied by a factor of 1/3. Okay, so they're the same direction. This one has length 1 and the other one has length 1/3. So to find the unit vector, all we have to do is we're going to say that is 1 over the length of v times v. So in this case, we've got 1 over 3 times 1, -2, to 0. And so this will be 1/3, -2/3, 2/3, 0. And this is the vector u that we're looking for. And so just to indulge that, u definitely has a length of v. If we were to determine, that we're looking for the length of v, again, it's the square root, or sorry, we're talking about u, it's the square root of u dot u. All right, so we've got now the square root of 1/3 times 1/3 plus -2/3 times -2/3 plus 2/3 times 2/3 plus 0 times 0. And that will give us the square root of 1/9 plus 4/9 plus 4/9 plus 0, which is the square root of 9/9, which is 1. So u is definitely a unit vector, and it does fall in the same direction as u because they differ just by our scalar. back on those properties we had a couple of slides ago. U dot U plus U dot V plus V dot U plus V dot V, which we can write as, since U dot V and V dot U are the same thing, we can write that as the norm of U squared plus 2 times U dot V plus the norm of V squared. Okay, now let's look at the distance between U and V. So if they're perpendicular, these two lengths are going to be equal. So the distance between U and V now would be U minus V dot U minus V, which we get U times U minus V minus V times U minus V, and that's going to give us U dot U minus U dot V minus V dot U, or U dot V again, and then minus times minus gives us plus V dot V, which we can write as the norm of U squared minus 2 times U dot V plus the norm of V squared. And so if these two guys are equal, then what we're saying when we compare the two equalities is that if we have orthogonal, then 2 times U times V, this term, is equal to minus 2 times U times V. And that's only true when U dot V is equal to 0. So we're going to use that for our defining characteristic of U and V being orthogonal. One other relationship that we can get from this is, I'll just look right here. Do you see how we have the norm of U plus V squared, and then we got it equal to this guy? But if we've said that U dot V is equal to 0 when we have orthogonal vectors, then we can also just make the little statement, the norm of U plus V squared is equal to the norm of U squared plus the norm of V squared when we have orthogonal. So we've got two little definitions that we can go by. This one is Pythagorean theorem, and this is just our direct definition of orthogonal.